Welcome to Group 12's Senior Design 1 project. Here we are representing the Mobile Aquatic Recorder, MAR. The overview for this project is going to be the project description, marketability, problem statements and objectives, intended users and usage, intellectual property, within others. This project focuses on building a small, low-cost, remotely operated underwater vehicle capable of collecting basic water quality data and live streaming video in real time. The system will use a sealed, pressure-resistant hull with a Raspberry Pi-based control platform, electric thrusters for maneuvering, and a tether that provides both power and reliable communication. A marketability analysis was conducted to evaluate the feasibility, demand, and competitive positioning of the mobile aquatic recorder. Comparable Kickstarter ROV projects were analyzed to establish benchmarks in pricing, features, and funding strategy. A marketability analysis was conducted to evaluate the feasibility, demand, and competitive positioning of the MAR rover. Comparable Kickstarter rover projects were analyzed to establish benchmarks in pricing, features, and funding strategy. The ROV Trident featured a $1,200 retail price, a funding goal of $50,000 managed to Kickstarter, a 3-thruster system with a wireless buoy communication, 3-hour runtime, and the target market was recreational users, educators, and light commercial mapping. On the other hand, Fathom 1 featured a retail price of only $600, with the funding goal being $150,000 through Kickstarter. It features modular, upgradable thruster designs, 1-hour runtimes with an 180p camera, and the target market was hobbyist educators, with a focus on affordability and portability. The market demand exists for compact, accessible rover systems, much like the MAR. Successful products emphasize wireless connectability, portability, strong camera capabilities, and a reasonable price range within $600 to $2,000, establishing a competitive baseline for us. Where does this leave MAR? There is a growing need for affordable, user-friendly underwater monitoring systems. Current professional-grade rovers are expensive, while recreational drones often lack research-focused functionality. The mobile aquatic recorder satisfies these needs by combining affordability, portability, and environmental focus. It builds on proven features seen by those in the Kickstarter projects, such as the wireless communication, compact size, and ease of use, while also targeting research and sustainability applications rather than just recreation. Just imagine students using this device to monitor reef health over time, researchers collecting consistent water footage, and communities gaining real visual evidence of environmental change. Current underwater monitoring systems are too large, expensive, and complex for small research teams or schools to use, making it difficult to connect basic water quality data and live video safely in shallow environments. This project solves that issue by creating a small, affordable, tethered underwater vehicle that can gather essential sensor data and stream real-life video without requiring a diver. There is a lack of affordable, accessible underwater monitoring systems designed especially for educational and environmental research purposes, limiting the ability of students and local organizations to study and preserve aquatic ecosystems.
Hello, my name is Steven Sedan, and I'll be presenting the operating environment for MAR. The RC submarine's performance, safety, and reliability are defined by its operating environments. Shallow freshwater and coastal core ecosystems impact material selection, as well as sealing methods, power management, propulsion, and communication reliability, which are all things that are important to the MAR RC submarine, as it will affect and also help us gain more understanding of how to properly integrate the materials needed and the safety procedures to ensure that nothing breaks and everything works functionally underwater. With a 50-meter depth goal and a 20 to 30-meter tether, the system is designed to ensure stable operation, accurate sensing, and safe deployment while meeting educational, financial, and projection constraints. Thank you for listening.
Hello. The intended users and uses will be tailored more to the educational side. We're going to take a step back from commercial usage and put a more emphasis on the hobbyists and students. This way, submarines and environmental safety and exploration can be more accessible to education and the general population. Here we have the background where we go and review 3 distinct and unique products. Within each of these products, they use different configurations of thrusters, as well as microcontrollers and tethered cords. To start off, we have the design and construction of an educational remote operated vehicle. In this scenario, it was a compact Raspberry Pi powered remote vehicle which used 6 thrusters in its alignment. To go in depth with the Blue Rove 2, which was a modular and open source professional grade rover. Here we used also 6 thrusters, which was equipped with a camera that had a 150 field of view scope of vision. And finally, we had a low cost submersible rover. However, you notice in each of these, there was either a lack of funding in order to add integrated sensors, or the budget was too high. We, however, are going to propose a different and unique submarine. In our submarine, we're going to try to implement environmental sensing as well as make it budget friendly so that the users can still explore underwater environmental safety.
When designing a product, engineers and designers alike must take into consideration ethics. While our team strives to follow the IEEE Code of Ethics, there might be some dilemmas that arise that are beyond the code. For example, people may assume that our drone is not environmentally forward. It can disturb natural wildlife through its sheer presence in delicate ecosystems, or through failures and normal wear and tear, it might degrade and contaminate the water either chemically or with the plastics that it is made of. Our team sought out to find 4 solutions using the ethical theory model. Presented here are the 4 solutions. First, we would ignore the concerns. Second, we would invest in stronger materials to reduce the chance of any breakage and chemical spillage. Third, be investing in more environmentally friendly materials so that in the case of a breakage, the contamination will be reduced. Lastly, we would wait until we see signs of wear and tear, and we would appropriately respond by reinforcing or redesigning the product. Beyond ethics, our product will also have social impacts, both locally and globally. Locally, we can help educators and researchers by giving them insightful data that can help prevent and preserve any existing coral reefs. Our data will help understand the effects of climate change and other human pollutants, and then this can scale to a global social impact by creating and reinforcing already existing movements to be more environmentally friendly. This device not only meets functional goals, but fosters environmental change and care. And our idea of the good life is to have an environmentally forward society that is determined on preserving our natural wildlife.
Hello, my name is Roberto Hernandez, and today I'll be presenting the concept development for MAR. Our goal, designing MAR, was to improve accessibilities for schools and small research teams lacking affordable underwater ROVs. In order to achieve our goals, we had to research multiple design paths, including autonomous vehicles, wireless platforms, and commercial-style ROVs. During this research, we eliminated many due to high cost, complexity, safety concerns, and poor performance. This led us into a realization that a compact tether system provided the best of reliability, real-time data transmission, and affordability. Our final design is going to be a modular, low cost, capable of capturing live video and essential environmental data. Our system design allows for future expansion and for flexibility for different research and educational needs. In conclusion, our MAR proves that effective underwater monitoring can be achieved through a compact, affordable, and reliable system. By integrating real-time video and environmental sensing, it proves an accessible solution for education and research. Its flexible and compatible design ensures adaptability and long-term value beyond the initial prototype. Thank you for your time. This concludes our senior design presentation.